We're now going to end this lesson with a practical demo example of building a scene in Houdini. So in the video here, you can see this lovely flowing cloth example, and I'm going to break down the scene that I used to build this. We're going to reconstruct it, and we're going to look at how to render this in the Lops and Solaris context with Karma. So let's dive in. So you can choose to follow along with me by opening this cloth example file, which should be included in the downloads, or you can rebuild the entire thing as I am building it now. Either way is totally okay. So you'll notice that we're starting with a scene that has already been set up, and I'm going to walk through this and we'll rebuild this, and feel free to change anything in here that you like, season to taste, so to speak. So let's kind of break down what's going on here. We've got a couple different streams here. We've got this stream right here, which is setting up a cloth simulation, and we're writing the simulation out to disk. And then we have a stream here, which is creating the actual high-res geometry that we'll be rendering, binding it to the cloth simulation, and sending that out to disk as well. And then further along, there is another network, which is built in Lops, which will be pulling in all of this data and rendering it out. I also have this little branch off here of a subdivide node, which is useful because what I'm doing here is subdividing the geometry at render time. However, in the viewport here, it's kind of ugly to look at and hard to know just how well that's going to subdivide. So I have a little subdivide node here just so that I can get a preview of what that's going to look like. You may be asking, why do I have two different streams? Why aren't I just rendering the cloth simulation as it is? That's a couple of reasons. This is more of a traditional workflow where you would do a lower resolution cloth simulation and then bind a higher resolution geometry to it, or have a cloth proxy that is different than the actual mesh that you will be rendering. You could definitely just render the simulation as is if you choose to. So it's sort of up to you. I just wanted to show you something of a more traditional way of working with cloth. Now let's go ahead and we'll dive in. So I'm going to just copy this grid here just so that we're starting with the same thing. So we're starting with just a fairly simple grid here. And what we want to do is prepare this for simulating. So I am going to be using a remesh SOP here. And a remesh SOP is a triangulation SOP. It basically lets you dial up and down some parameters, here basically the target size, to control how subdivided this geometry is. The reason I'm triangulating this mesh is because if you're using a quad mesh, then your folds in a cloth simulation are going to be biased to the geometry, to where the edge flow is. So, for instance, this piece of cloth could only bend along these edges. If you triangulate it, you get a bit more freedom in terms of how the geometry is going to be bending. So that's the reason that I'm triangulating that here. If you don't want to triangulate it, you don't have to. You could work with a very dense mesh as well. You could just make this something like 100 by 100 or whatever you need to do. Just keep it square. All right, so let's find out what our settings were. Here we're going 0.05. So a fairly dense mesh. That's really dense for a simulation mesh, at least while we're setting some stuff up. So what I'm going to do is just put a little multiplier in here, and I'm going to multiply that by 3 so that we get something that's a bit more workable while we just set everything up. And when we're ready to run our simulation, we can just delete that out of the target size there and just keep our value. So I want to have 3 of these. So what I've done here is use a copy and transform, and that gives us 3. And they're offset from each other. So here we go. We have 3 pieces of cloth. The reason I do it this way is so that we don't have to run this remesh operation through more geometry than we need to. We're only running that once and then just duplicating the results here. When I copy this on here, I also would love to be able to identify the copy number that's placed on here. So what I've done is I've enabled this copy number attribute, and I've written my own attribute in here called layer. When I right click on here and go to our spreadsheet, and you go to the primitives here, what you're going to see is there's an attribute here called layer. And as we scroll down, we can see that we get a different value assigned to each one of these pieces. So this is useful to help us identify which piece is which, but also the solver can use this as well so that it can figure out solving order when things get stacked up or colliding with each other. It's not necessary, but it is helpful. Now we're going to set up cloth constraints on here. So Vellum is the cloth simulation tools in Houdini, and there are a lot of them. If you tab here and you type the word Vellum, you're going to see there are a lot of different things in here. For now, we are going to choose Configure Cloth. And it's a required input. On the first input here, all we need to do is wire our geometry straight into Vellum, and you'll see we get a whole bunch of these white lines. And these are showing the connections between all of the points in the geometry. We further can look at how this is calculating a couple things, especially thickness. So if we visualize thickness, what you're going to see is that each of these points has a little sphere around it, which shows the approximate thickness of this piece of cloth. So you can change that if you need to. You can adjust things like the edge length scale if you wanted to tweak this. You can set it uniform if you want, so that even when you change the edge lengths of the underlying geometry, the thickness doesn't change, or you can just let it calculate automatically. I'm just going to choose calculate. Let's see, what do we have it before? I think it was calculate uniform. Let me just double check what's on our other one. Yep, right there. We also will be defining pieces from connectivity. What that means is that instead of treating this all as one mesh, it will be treated as 3 different meshes because they are disconnected from each other. All right. The other reason why we called that layer attribute up here layer is because Vellum is actually looking for a specific attribute called layer so that it can perform some optimizations in terms of the solver. Here you could define a specific layer and write that attribute out for the pieces of cloth if you wanted to. Now, we're not going to deal with any of this other stuff just yet, but here's where we would adjust things like the stretched properties of the cloth, and then we also have the bending properties of the cloth. When we get a little bit further into the simulation, you'll see that we're going to adjust some of this stuff. Finally, we need a cloth solver. Yes, there's one other thing we need to do. That attribute that we had here for layer, we're going to want to promote that into a primitive attribute. So why don't we take a look here? If I middle click here, you'll see that, we don't want to promote it to a primitive attribute. We want to promote it from a primitive attribute into a point attribute. So you'll see that right now it is a primitive attribute, but we need that to be on points. So we will use a tool called attribute promote. And the original name here, we want to make sure we are at primitive and then to point. Now we can find it. It's called layer, and that's it. Now we have promoted that attribute, and instead of it being a primitive attribute, it is now a point attribute. All right. Now we can put a solver down. So we're going to use a Vellum solver. And you can see that the first 2 inputs are required. The first is the geometry that is being simulated. That's right here. And then the second input is the constraint network that is generated from the pink output here. If you put a null down like this, which is a do nothing node, you can actually take a look at the individual outputs. So you can see here, that's our cloth output. If I wire this in here, that is the constraint network that's built to handle the simulation data. So I'm going to wire this in. The third input here in both of these would be for any collision geometry that you want to use in your simulation. We're not using any, so we can either leave this out or we can pipe it in. It'll be ignored since there is no data coming in here. And that's all we really need to make a simulation. Now I'm going to press escape and cancel that because my frame was set to 134 instead of frame 1. You might want to make sure you're parked at frame 1 here. And now if I just kind of play through this, what you'll see is a simulation. The cloth is falling, but there are no forces. There's nothing to collide with, so it's a pretty boring simulation. So we were kind of going after a zero gravity feel in here. So one thing we'll want to do is take our forces here, and here's gravity. We're going to just zero that. Now when I play, you'll see that nothing is happening in here. So we have this nice turbulent force going on in the simulation. And when you look at the forces here, you have wind, which is directional wind. You don't have anything that's like, give me this nice swirly force. So what you would do is you would go inside the simulation, and here you can plug in forces. So you can pretty much do anything you want as long as it's outputting forces in here. And most of the tools that you will be using will be particle forces. If I tab here, I'm going to skip most of this stuff, but you'll find most of the useful tools you'll need here in pops, which are the particle forces. I'm going to find a pop wind force, and I'm going to pipe that right into here. And I don't exactly know what the settings are that we're going to need, but we'll take the amplitude and we'll put that up at something like 2, and we'll take the swirl size at 2 and maybe make the pulse length at 2. So amplitude is how strong is this noise field. So that's noise that we're using. Swirl size is the actual physical size of the pattern, the noise pattern in there. And then the pulse length is how quickly does that pattern evolve over time. Now, once I start playing this, you'll see now that we get a nice simulation happening. All right, so that's looking okay for now. What I'm going to do is go inside our other network here, the Vellum solver, and we're just going to copy some stuff out of it. So we do have a pop attract node, and I'll get into that in just a minute. So first we're going to find our pop wind, and we're going to see our amplitude is 3, swirl size 3, pulse length 2, and roughness 0.3. Rather than just copy every value and try to remember it all, I'm just going to copy and paste this node for us. And then we know our settings are exactly the same. Okay. Now you'll notice that I also have this little checkbox here, use vex expressions, and I have a little expression in here. Let's disable that for a second, and then I'll explain what that's doing and why we're using that. So when I play through the simulation, one thing that I don't like about this, and that I think makes it less interesting, is you'll notice all the pieces of cloth are all bunched up and gathered together. And of course, it's natural. They're all being influenced by noise equally, and they're all sharing the same locality of space for that noise. So we get this kind of bunching up, everything feeling like it's all stuck together feeling. Now, that's not something creatively that I wanted here. So my solution here was to actually take our layer information that let us know which piece of cloth was an individual piece of cloth. We had something to identify them with, and offset the noise value for each of those pieces. In effect, what that does is it slightly alters the force that's being applied to each piece of cloth individually. However, because they're all part of the same simulation, they can all work together and influence each other. So I use this vex expression here. I turn that on. And what I did is I targeted this parameter here called offset. Now, if you kind of hover over here, what you'll see is it tells us the actual name of the parameter, and you'll notice that it's a lowercase o there. And it says offset 1, 2, 3, and 4. But when you're referencing it in here, you can use offset and then .x, y, z, and I believe that last one would be w. I'm going to copy this out of here and just show you one thing here. There are a couple presets that you can do in here as well if you needed to. They'll give you some good information. All right, so what I've done is I've said, I want the offset x to ignore whatever is in here. Instead, what I want the value of that to be is the value of our layer attribute, and we'll multiply that by 2 just to really offset that. So layer 0 is going to be 0, layer 1 is going to be 2, and layer 2 is going to be 4 as the offset. Now, when we look at this force, what we're going to see is that the cloth values, the noise parameters here, are actually offset from each other, and it's creating a slightly different force between each individual cloth layer. And so now they don't appear to be stuck together the way they were before. Now, whether this is natural or not isn't really a concern of mine. I'm going for something a bit more artistic. Now, if you play this simulation through long enough, what you'll find is that the cloth, depending on the force that you have, depending on the parameters that you have, it's not necessarily going to stay centered in the screen. You'll find that it's bouncing around, pushing around, things are separating, and they might not artistically do what you want them to do. So what I wanted to do is create a force that would also bring everything into the center of the screen. So I'm using something called a pop attract force, which is going to just create a force, like I said, that's going to attract to a location in space. So let's go and find that. I'm going to go back into my Vellum solver, and I'm going to just copy this pop attract out of here. Now, I'm going to go to goal, and you'll see that I am putting our goal position here right in the center of our world at 0, 0, 0. And all I have here are a couple things. One is the scale of the force that's being applied, and the other is this reversal distance. Reversal distance is the distance at which that force no longer is an attractive force, but starts being a repulsive force. The reason for this is so that things don't just bunch up right in the exact center at 0. They kind of want to come close, but then they sort of stop coming close when they get within a certain distance. If I disable the pop wind and I play through the simulation, you'll see how this behaves. Right, so it's easy to see what that force is doing. It's a very small, very subtle force, but it's pulling everything into the center of our world. So I'm going to turn that pop wind back on, and you'll see the combination of all of these together. All right. At this point, we can go and start adjusting some of the cloth properties. Now, let's take a look at our vellum cloth here. One thing you'll notice, by the way, as you scroll up and down and look at parameters, is anything that is bolded here is something that has been altered from the default values in a node. Now, what I want to do is find out what I have done with bend, because that is the only thing that I've really changed. I wanted to make this cloth much more bendable. As you notice, it looks a bit stiff, a little bit rubbery. So what I've done is I've taken that value and I've brought it down pretty significantly here by using this multiplier. So I'm going to go to my vellum cloth here and I'm going to find the same one. Let me just check. And yes, that should be the same. Now when we play through our simulation, we should see that it bends a lot easier. Now, this isn't going to be quite as easy to tell because the resolution is still very, very low, but you'll notice a difference when we switch to a high resolution simulation. And I'll go through that again when we get to high res. Alternately, I did a very, very small thing here, just in terms of the solver. Our simulation is fine. I typically wouldn't be changing some of these specific settings unless I needed to. These are things that control the accuracy of the simulation and are a bit more outside of the scope of this demo, because then we have to get really deep into cloth simulations and optimizing them, and we're not going to do that right now. But what I've done is I've taken the constraint iterations here and I've just put that in half, and it's just to get a bit of a quicker solve. So you'll notice when we dial that down a bit, it's a bit faster to simulate here. Not quite as accurate, but for the sake of our demo, it should be just fine. Now, what I want to do is go back to our remesh, and I am going to delete that multiply by 3 out of here, and you'll see we have a very, very high resolution simulation. I'm going to turn this onto smooth as shaded. I'm going to play through the simulation a bit, and you'll notice it's going to go much slower here. But you'll also see, because of the density of our geometry, you can start to get some things like these really nice fine wrinkles in here. There's lots of detail in the simulation, and the reason we're getting all of these nice wrinkles is because we adjusted that bend stiffness of the simulation of our geometry. So the geometry actually can bend quite easily. It can't stretch, but it can do the bends. Now let's take a quick look at what that parameter did for us, the bend one. So I'm going to go back to our vellum cloth here, and we'll go to bend, and instead of this, we'll put it maybe at like 0.01, and I'm going to play this simulation again. And what you'll see is that a lot of that fine detail has gone away because the cloth is being told you don't bend as easily as you did before. So that parameter is really useful to control the look of your cloth, right? Is it silky? Is it something a bit thicker, like wool? Is it made of plastic? Is it a plastic bag or something like that? Right? You can see the detail is just gone from there. And it's because we've told the solver that this doesn't bend that easily. So I'm going to go back to this, and we'll put that back at that value here. Now, in theory, I will have gotten all of that stuff matched up from here. And the last thing that I need to do is write that simulation out to disk. So one thing you'll notice, I'm going to put a little null down here so that we can take a look. When I middle click here, you'll see there are a lot of attributes here. There are a ton of them. And when we write this out to disk, what's going to happen is all of those attributes that are on these points, right? There's a lot of attributes and there are a lot of points. We have 88,000 points here. These are all going to be written into that file, and it's going to make the file much bigger than it needs to be. It's also going to make it slower to read. When we need to read that data back in, it's going to take up more space on our hard drive. So typically you want to dump any unneeded attributes before you write off to disk. So what we have here is an attribute delete, which is going to delete any unneeded attributes. So I'll show you how that works. Just going to put this down here, and you can manually select the attributes you want to delete, like force and mass and everything, but that's quite intensive to have to do that. It can be a lot easier to use these wildcards. So we can say for point attributes, delete everything. Star is everything. And then we can say except, which is that little caret symbol. We would like to keep position. You don't really need to say that. You can't delete position out of geometry, but still, I like to do that just to, I don't know, give me some peace of mind. I'd like to keep any velocity information that's part of there. I'd like to keep any UVs that might be assigned to our geometry, and I'd like to keep any normals here. We also had that layer attribute, which is going to be very useful for us at some point if we need it. And that might be everything here. For our vertex attributes, we don't have anything. Primitive attributes, we can delete that dop object attribute and detail attributes. Most of this stuff is not very useful, so we can delete it if we really wanted to. Now, when I middle click over here, you'll see we only have layer, position, velocity. We still have point groups and prim groups, which if we wanted to, we could delete those too, because that adds additional overhead. And for that, that would just be a group delete. And we could delete everything. So no more groups there. We'll just check here. We pretty much kept all the same stuff. And then we are ready to write this out onto disk. So for that, we're going to use a file cache. We'll put this down here. There's a bunch of stuff already in here. I'm going to disable this constructed thing here. So what constructed does is it basically creates all the file paths for you so that you're not manually writing in stuff. All you would need to do is just give it the base name of what you wanted to write. So this could be, cloth sim. It'll put a version number here. It'll put it in this folder, and then you just click save to disk and it'll write it out for you. However, I don't really want that. I would like to write my own path in here. If you ever wanted to see the constructed path, this shows you, by the way, where it would be. So you'll notice it'll go into my tutorials, into Geo, ClothSim, version 1, ClothSim, write all of that stuff out. I'm going to change that to explicit, and now I can put my own path in here. So it's going to go into my local Houdini directory where this project is, into a folder called Geo. I'll change this to something like ClothSim. $F is necessary. That stands for frame. So what that means is every time we get to a new frame, it is going to write a unique individual file there. And then we need the file format type. So .bgeo is the Houdini geometry, the binary geometry file format. And then this .sc is a compression algorithm that gets applied afterward. So you are almost always going to be writing geometry out as .bgeo.sc in here. But this $F is absolutely necessary for you to write out a sequence of images. Otherwise, it will just keep overwriting the same geometry over and over and over again as you advance through the simulation. Here we can set our frame range, and when we're ready to save it, we just click Save to Disk. So here is what I had written out previously, and you'll see I had changed the geometry file name. Here it was called Vellum Sim. If I go in here, you'll see we've got two geometry sequences here. I have my Vellum Sim, and then I have cloth. I can disable this, and we can actually see that there's a bunch of individual files that are making up everything. And when I play this back, you'll see that we have this high-res simulation. Now that covers the simulation part of this. What we'll do next is we'll learn how to bind high-res geometry back into this simulation.